Below me lies a city bustling with activity. But London's busy life poses a set of problems that its inhabitants have been trying to get to grips with since the very beginning. How do you find enough power to heat the homes and run the business? How do you get clean water in and waste out? If we hadn't solved those problems, London would never have flourished and become the great city that it is today. The Romans got most of their water from wells, and obviously they got a bit bored of pulling it up on buckets on strings, and so they built a machine to do it for them. And this is the Museum of London's reconstruction of a Roman water-lifting machine. Now, in Roman times, they would have had slaves or animals to push this thing round, and I guess I'm one or the other, and it's quite hard work. But you'll see I'm turning this capstan, and that's turning a cog there, and that's turning another cog over my head, which is turning the shaft, and that's lifting these buckets on the left-hand side. They're oak buckets and iron pins and an iron chain. It's very remarkable because each bucket holds about 7 litres of water, and the well was about 5 metres deep. And this single system was enough to provide water for about 8,000 people every day. You can see I'm pumping quite a lot of water up over the top, and at the moment it's just running back down into the tank underneath. What's very cunning is that because the buckets are held on with pins, they could just take one of the pins out and put in an extra bucket, or take one out. In other words, lengthen or shorten the chain, which was important because if the water level in the well was low, they'd have to go down further to get it. And if the water level rose, they didn't want the buckets going too low into the water because they then begin to oscillate and it didn't work properly. Very important, they just skimmed the surface. And just look at that enormous amount of water that I'm lifting up.
As well as building remarkable pieces of machinery like this, the Romans were also the first to use pipes to channel water to where it was needed.
After the fall of the Roman Empire, the Brits stopped using pipes for their water. They relied on springs and streams and the river, of course. But by the beginning of the 13th century, the population was growing and they needed a better supply.
In 1237, they built the Great Conduit, a system of pipes that brought water from the Tyburn stream 2 miles to the west of the city. Lead pipes took the water downhill via the Strand, across the Fleet River and along Cheapside to the Conduit House, where the water would be collected. In 1994, while BT were digging a service shaft, they found a medieval chamber that would have been directly below the Conduit House. I was invited down to take a look.
Wow, that was quite a tight fit, but I'm now down here in this chamber. The beeping that's going on is telling us that we've still got some air to breathe, for which I'm very grateful. And this is Mark Birch, who's a senior archaeologist at the Museum of London. You actually dug this out, did you?
I did, yes.
Yes.
In summer of 1994.
Right, and we're not, what, about 10 feet down below street level?
About 3 metres down from street level.
Right, so there must have been quite a flow of water if it was going to fill a chamber like this.
Yes, it was gravity fed all the way,
right,
but it was coming down the slope all the way.
And did people sort of meet there for, chats and stuff?
Oh, definitely. I mean, the Great Conduit, as this became known later in its life, was recorded as being somewhere where people would meet. It was in the Market Square area of Cheapside, and people would congregate here. To supplement the supply they would have had from their wells, they would have come down here with jugs and pitchers and taken the water they needed for their daily use.
Oh, terrific. And so how long do you think this was in use?
Well, we know from records it was in use certainly up to the Great Fire in 1666.
Right, so that's 400 years.
It must have been, yes.
And it's fabulous construction, isn't it? I mean, it's in very good nick. It could do with a bit of repointing, couldn't it? But frankly, and that's just lime mortar holding it together, is it?
Yes, it's a lime mortar with plenty of aggregate in it. It's almost a concrete, bonding the green sandstone, bits of flint and tile.
Yeah, are those Roman tiles? It looks awfully like...
Yes, they actually are Roman tiles, but they would have found those lying around.
Yes.
In London.
That's so characteristic, aren't they, these thin tiles?
Yes.
More and more conduits were built, bringing fresh water into London. But the River Thames was still the main source, despite being rather less than pure.
The process of slow sand filtering was first used by the Chelsea Water Company in 1829. They wanted to take water from the river, the Thames, and they realised it looked a bit like that, and clearly that's not fit to drink. So they developed a really simple system. And what they did was to take a filter bed like this, and they put in first big stones at the bottom. Next, they put gravel on top of the big stones. And then on top of the gravel, they put sand. And I'm just going to dump this on top like this. And I need more at my end over the hole, but I'll put some at the other end too. And then it needs to be patted down a bit. And so we've got 3 layers, and the water will go first through the sand, and then through the gravel, and then through the big stones. And the idea is that the sand should take out at least of the big lumpy stuff on top. So I have a clean glass, which I'm going to put underneath. And the theory is that when I pour in this foul water with all that gunk in it, it should come out crystal clear and ready to drink. All the big rubbish has been taken out, and all we're getting through is some very, very fine sand. And once it's settled down, it should come out crystal clear. Now, what those early practitioners didn't realise was that it wasn't only physical filtering, there was also some biological filtering. Because on top there, you collect some bacteria known as the Schmutzdecker. And those bacteria are actually helping to clean up the water. In fact, it was so efficient that the same system is still being used today. There. Your health. Well, maybe later.
In 1852, it became a legal requirement for all domestic water to pass through a filtration bed before use. These new filter beds were often accompanied by brand new pumping stations to pump water directly into homes after the filtration process. This pumping station is in Stoke Newington in northeast London. Its pumping equipment has long since gone, but the magnificent building still stands.
The filter beds were across the road where those houses are now. And then, because this was a posh area, they didn't want to build an ugly great pumping station, so instead they built a Scottish castle. Isn't it wonderful? It all looks decorative, but actually it was all functional. The great big high tower in the middle was a chimney. The square one on the right was a water storage tank. And the pointy one on the left was actually a place to give access to the huge beam engines. Even those buttresses on the right-hand side, which look as if they're holding the building up, were actually space for the huge flywheels connected to the beam engines. Isn't it terrific?
Cleaner water was coming into homes, but in the mid-19th century, as the flushing lavatory became more and more popular, wastewater became a problem, especially as it flowed directly into the Thames.
Eventually, Parliament realised they had to do something about the sewage, and they gave the Metropolitan Board of Works £3 million, fantastic amount of money in those days, and told them to sort it out. Well, the chap in charge was Joseph Bazalgette, who was a wonderful man with an enormous luxuriant moustache, and he designed a great system of intercepting sewers, 3 to the north of the river and 3 to the south. And they all flowed from west to east, and they came together at Abbey Mills in the north and at Crossness in the south, which is where we are today. It was a vast undertaking, the biggest engineering project anywhere in the world at the time. Well, by the time the sewage came here, and it came all the way by gravity, just trickling downhill, it was way underground. And what they needed was to get it high enough that they could discharge it into the river at high tide, so it would be swept out by the outgoing tide. So here they built this great building with 4 huge beam engines to pump that sewage up. And one of those beam engines has been restored and it's running today.
It's now the largest surviving rotative beam engine in the world. The steam flows through the cylinders and the piston rods drive one end of a 42-foot-long beam. The other end turns the 28-foot diameter, 50-ton flywheel. Plungers attached to the middle of the beams could pump up to 17 million gallons of sewage every day to Crossness's subterranean reservoir. From there, it flowed out to sea on the tide.
This building was opened on the 4th of April 1865 by the Prince of Wales. But it wasn't just the Prince of Wales. There were 2 other princes, a duke, 2 archbishops, and the Lord Mayor of London. They were fantastically proud of this building, and once they'd started the engines, they went outside and had an enormous lunch. Which reminds me, it's about that sort of time now. Anyway, this was the biggest engineering project in the world, and 90 or even 95% of it was underground. Poor old Bazalgette, he'll never be famous like Christopher Wren. When he did come above ground, he made the most of it. And here he's built an absolute cathedral in cast iron. Look at this, hollow pillars. And then up above, terrific tops with leaves and fruit and goodness knows what. It's like a cathedral, it really is. And this place is only for pumping sewage. And then look at these terrific screens. You know, leaves and flowers and intertwined curly bits, and everywhere the symbol, the logo, if you like, of the Metropolitan Board of Works. This is a true monument to excrement. Before 1800, people used to light their homes using candles like this one here, or oil lamps like that one up there. And both these things work on the same principle, using a wick. One of the interesting things about the candle is that the solid wax won't burn. The only thing that burns is wax vapour. Let me show you. Can you see the flame jump? It'll jump back down to the wick from the taper. Because when you blow it out, what comes off is not smoke, but wax vapour. And the heat from the flame is melting the wax, turning it into liquid. The liquid goes soaking up the wick by capillary action, and when it gets hot, it turns into vapour, and that's what burns. And the same happens with the oil lamp. There's oil in the reservoir, it soaks up the wick, and it burns at the top. Now, both of these things are quite complicated. You have to go out and buy your candles, you have to go out and buy your oil, you have to scrape up the remains of the candle wax that drips off the side, and so on and so forth. So when gas began to be piped into people's homes, they were absolutely delighted. In this perfectly preserved Victorian house, they still have gas piped, so it comes out of the walls. And if you want a higher flame, you can turn it up, and a lower flame, you can turn it down. Isn't that wonderful? But then they wouldn't just have had a naked flame, they generally surrounded it with a glass chimney like this, partly because that helps to diffuse the light and it looks prettier, and partly because it helps to prevent the flame from blowing out in a draught. In Victorian times, in fact, that flame would have been a whole lot brighter.
Victorian gas was much dirtier because, unlike today's natural gas, it was made from coal. All that muck and dirt in the coal would make the gas burn with a much brighter, yellower flame. The gas was made right here in London and was known as town gas.
I'm going to try and make some here with the help of John Gibbons, who's a senior lecturer here at Imperial College. So, I'm going to take some coal and I'm going to put that in a kettle. And that should be plenty. And then I'm going to heat it on this burner. And in those days they used great big retorts to heat the gas for the whole town, and actually some of those were called kettles. And what happens is the heat breaks down the coal and you get gas coming off. The first report we have of coal gas comes from a chap called John Clayton, who was rector of Crofton Parish Church near Wakefield. In 1687 he made a trip over to Wigan and found a ditch wherein the water seemed to burn like brandy, and the heat whereof was so strong that several strangers were seen boiling eggs over it. Well, he dug down and he dug out some coal and he went home and heated it up and he got coal gas, which is what, look, we've got coming off our kettle now. Do you think that'll burn?
Well, let's give it a go. It'll burn soon, I think.
Not yet.
Not yet.
So basically what we've got coming off here is steam. This is water because all the coal was very wet. And as that boils off, so it'll bring with it the coal gas.
Yeah, when it goes green, it'll burn. I think it's still a bit clean yet.
Okay. Now, natural gas is just methane, but coal gas is a mixture of methane, carbon monoxide, hydrogen, and all sorts of other things, including sulfides, hydrogen sulfide and other sulfides. So it was very smelly and very poisonous. And the natural gas we have today is almost not smelly at all. They have to add some smell, so you notice if you've got a gas leak. still just water coming off, I guess.
Well, it'll be the first volatiles don't burn very well. There's a lot of carbon dioxide comes first.
Right.
And as it gets hotter, you get the tars and what they call the illuminants, the bit that makes
Ah,
it
it's
shine.
getting more interesting, isn't it? Yes, try that. Ah, there it goes. That is terrific. And all the yellow is a mixture of tar and the sulphury things, isn't it?
Yeah. I think the stuff that's looking sort of brown is some of the sulphur, but that's a pretty clean coal as well. They'd have used much worse coal in the old days, but because that's sold now as burning in grates, it's not too bad.
Right.
Gasworks appeared all over London, even in places as central as Pall Mall. There's nothing left of any gasworks themselves, but you may have seen the enormous gas holders built to contain the town gas. They worked so well that some are still used today for our natural gas. The gas holders are made up of a number of huge metal tubes that slide up into themselves like a telescope. When gas is pumped in, the container will rise. If more gas is being used than is coming in, the holder will gradually fall.
Throughout the beginning of the 19th century, gas became more and more popular and lit more and more of London's streets and homes. But then it began to run into competition thanks to an invention by this chap, Michael Faraday.
Michael Faraday was born in 1791 in Newington Butts at the Elephant and Castle. The son of a blacksmith, he wasn't a wealthy man, and he had to educate himself. Faraday won a position at the Royal Institution and carried out chemistry experiments, but became famous for his work in the fields of electromagnetism and electrochemistry. Batteries had been around since 1799, but in 1831 Faraday created a mechanical means of generating electricity that would change the world forever.
What Faraday did was invent an electrical generator. And I've got a mock-up of his experiment here. What I've done is to wind copper wire around this tube. You see, it's a hollow tube I can stick my finger in, and I've wound about 100 turns of copper wire around it, and they come together and are connected to this tiny little LED here. And if I put a magnet inside, here is the magnet, put it inside the tube, as it moves through the tube, it will induce an electric current in that copper wire. Now I'm going to put a cap on the end, and then I'm going to shake the tube up and down so that the magnet is moving backwards and forwards. And if you look very carefully, you should see the bulb light up. Look! Look! You can see it glowing. I know it's not very bright, but with a bit more wire and a bit more shaking, we'd be able to light the whole of London. And indeed, that's what happens, because that is how all our electricity is generated today. Well, not by chaps shaking magnets, but by magnets moving through coils of wire.
Early electric power stations were quite small, but when the national grid was set up in 1938, huge power stations were built across London to cope with demand. The now derelict Battersea Power Station, built by Sir George Gilbert Scott, was the first of the new national grid stations. But even before the national grid was set up, some electric light had made its way into London. I went along to the Institution of Electrical Engineers by Victoria Embankment, one of the first places in London to be lit by electricity.
In the early 1800s, the only practical way of turning electricity into light was the carbon arc. And I'm going to make one here. Now, I know it's very bright, and so I'm going to put on these rather cool shades. I've got two carbon rods here, one here, and they're connected to an electrical supply. And if I touch them together, I'll get a short circuit, but then I'm going to take them just a few millimeters apart. Just watch what happens. You get this amazing arc, which is just electricity jumping across that gap from one rod to the other. Now, the real problem with this is that it's much too bright to use in the home. It would just dazzle everybody. There's also a technical problem. You can see that the rods are burning away because of the enormous amount of energy there, which meant if you wanted to keep one of these going, you had to devise complicated mechanisms to keep moving the rods closer together. Nevertheless, they were used in some lighthouses. Michael Faraday went and experimented at South Foreland, and later Dungeness had a carbon arc for a lamp. But for domestic use, they were really no good at all. The problem of domestic lighting was eventually solved by incandescence. That's passing electricity through a filament so it glows bright enough to make a good light. And that means about 2000 degrees. Now, Faraday and all the early Victorians knew about that, but they couldn't find a material which would work for them. For example, if you pass electricity through a copper wire, it will warm up to about 1100 degrees and then it melts. And that's not nearly bright enough. But eventually what they did was to put filaments in bulbs and pump the air out so they couldn't burn, but they still needed a material that wouldn't melt. And the two main inventors chose carbon. Now, there was the American Thomas Alva Edison, and over here, a chemist in Gateshead called Joseph Wilson Swan. Edison thought he could do it with fibres of bamboo, which he carbonized, that's like making burnt toast, and then put in the bulb, pumped the air out, switched on the electricity, and it didn't work. They always found hot spots and burnt out. Swan realized that what you needed was homogeneous fibres that were exactly the same, and he made the first ever synthetic filaments, carbonized them, put them in bulbs, and they worked. Edison tried to sue him, and Swan said, "Don't be ridiculous, I've been making these for years," and eventually they combined forces to make the Edison-Swan United Electric Light Company, and that's why we now have light bulbs, and instead of carbon, we use tungsten as the filament. But we still have to thank Joseph Wilson Swan.
Today, our city thrives on electricity. What was once a luxury, we now take very much for granted. Wasted energy in the London area alone creates over 3 million tonnes of carbon dioxide every year. That's enough to fill Battersea Power Station nearly 2,000 times. Perhaps we should think again about how our energy is produced and used if we are to safeguard our future.